Okay, so it's 3:15, right? So we'll make a start. I'm trying to see how many people in this class right now. Okay, 65. I think we should have around um, 90 people in this class. Anyway, let's make a start, right? So good afternoon to everyone. So we're going to look at simple equations this afternoon. I think sometimes the textbook will qualify this a little more and say simple linear equation, right? Linear meaning that, well, somehow you can relate it to a straight line. We will talk about that as we go on, right? Sometimes you see that simple linear equation or linear equations. And the whole idea is that you're talking about equations with just one unknown and well, there's no power on the thing, there's no power on the unknown that somehow will make it non-linear. um Let me go back to one of the axioms that we were talking about last week. And simple equations basically, all right, let me just throw up one there wildly, right? Let's say you have to solve something as simple as, all right, something as simple as that, right? Good. So there is a one of those axioms, real number axioms, and this axiom came under what we call the order axiom, right? Um, and basically, this is what it says. It says that if A is a real number and it's greater than B, and then you have another real number C, right? Then A plus C will be greater than B plus C, right? I think the axiom is referred to as the monotonicity axiom, right? What it's actually telling you here is that if you have this relationship going on, right? A is a number greater than B. If you were to add the same, you add a number, another real number to both sides, this balance, this balance will be maintained, right? It will be maintained. Well, what we're going to do, we're going to draw, well, the solution of simple equations draws on this. It's not using this exact axiom, but there's something called a corollary, right? Basically, it's like it's not a new axiom. It's not, sometimes you get what you call um, a theorem, and then you have a corollary coming out of that theorem, meaning that it's a consequence of. It's kind of a no-brainer then, right? That you can get from that theorem. So what really we're seeing here is that, okay, if this is so, in a similar way, if you have A is equals to B, then adding, I mean, these are not, they can't be two distinct numbers, right? They have to be the same for them to be equal. So if you were to add to one side something and you add to another side something, right? Then the balance is maintained, right? Similarly, if you were to subtract something from one side and subtract something from the other side, the balance is maintained, and so on. If you multiply one side by something and multiply the other side by something, the balance is maintained. And that's why I think in high school, the teachers use a very good analogy and say that, an equation is like a scale, that is balanced, right? And the solution of it lies in maintaining that balance. So what you do to one side, you must do to the other side, right? And if I'm to, let's say we go on, you have that same equation to solve. Maybe, okay, x plus 2 equals 7, right? Basically, if you want to solve this, you say, look, I want to find x, right? So I need to somehow get rid of that 2 from that side, right? So what we do to this side, we have to do to this side. So you do this, you subtract the 2 here, but to maintain the balance, what do? You take the 2 from the other side, right? And this here works out to give you 0. You end up with x equal to 5, right? So it's all based on that same little axiom there, that an equation is like a balance, a balanced relationship, right? And what you do to one side, you must do to the other side to maintain the balance. I know that basically nobody does this, right? Nobody does this. A lot of shortcuts have been developed and so on. People will just say, oh, and this here implies that x equals 7 minus 2, right? And therefore x is equal to 5, right? Isn't that what most people do? They do the shortcuts, right?
Yes,
Nothing's
sir.
wrong with
Yes,
that.
sir.
I'm just drawing your attention to what you really did in effect, because there is no operation like, okay, you say take over the 2 and it becomes negative. Where's the mathematical basis for that? If you understand what I mean, um there's no mathematical operation where you say, or you take over 2 and it becomes positive 2 becomes minus 2, right? In effect, what you're doing is this. It's just a shortcut, an acceptable shortcut. Everybody understand that, you know what? Mentally, you have done the arithmetic and it boils down to what's happening here, right? It's like you finish doing this part here and you're left with x equals 7 minus 2. So you're just going straight there, right? So yes, you can do that. That's not a problem, but you must know what you did, right? Remember, everything you do, all the equations you're going to solve, and so the inequalities, and so you're going to solve. You want to ensure that none of the rules, the axioms, right? It's a fancy word for the axioms, right? These are like the ground rules, then, the ground rules, right? Um, if once you don't violate any one of them, you are right? And that's a very good thing about mathematics. There are no contradictions in it, right? There are no contradictions in it. Mathematics is the only subject now that you hear the word theorem still being used, right? Um, for those science students in the class, right? It's only mathematics you're hearing of this until today, right? In the other sciences, you're hearing of theories, right? And the simple reason, mathematics is so solidly built. It's so solidly built, well founded, well defined, such that we can, use something, a term as grandiose as presumptuous, I would say, as this here. That this thing is a theorem, meaning that no other thing that you come up with later on should contradict this, because this is a universal truth. That's what a theorem is, right? Whereas in the other sciences, right, they talk about this because the knowledge changed so fast, right? What was believed 100 years ago, most of it they throw it out now. They're questioning everything, right? And that's why you have new theories emerging every single year, right? And none of them is going to say, you know what? Well, this here is an established fact, and that this could never change. Just to give an example, Newton talked about gravity. He talked about gravity. Well, before him, it was believed that all the planets and so were held together by like glass spokes. They didn't know the material, but they said, man, it looked like something holding the planets together. And so I think that was Aristotle. And everybody believed that. And so until, Newton told them that, look, no, the earth and all the heavenly bodies are actually held together by a force called gravity, right? And he came up with a law of gravitation that quantifies, right? He did call it a law. He was bold enough. In those years, you could have called things laws, right? You all hear of the gas laws and law of gravitation and all of those things. You don't hear these things in the sciences nowadays, When I say you don't hear them nowadays, meaning people coming up and say this is a law. Long ago, they will use these words, laws, because they feel that what they found out is the absolute truth. Nothing that they find later is going to contradict it. Lo and behold, with the people like Einstein and so, Einstein is saying no, that there is actually something like, okay, this is the sun here, and this is the earth here, and there is a fabric, right? It's a fabric, like there's a fabric, and the fabric of space and time, right? Because of the size of the sun, it kind of causes a depression in the fabric like this, and that is why um, the earth is being pulled towards the sun, right? So that and people embrace it a whole lot. People, as a matter of fact, everybody would talk of this thing as though it's a fact. It's a theory, right? It's his theory of what's going on, right? And he talked about relativity and the curvature of space and time and all of that, right? So he nor nobody is going to say, that is a fact. It is a better, I mean, it explains the behavior of planets and so on. Because somehow there's always that one, Newton and I was wondering that, man, there's no material between the sun and the earth, and you feel that a force needs a material to transmit its effect by, right? People feel that way, right? So, and well, then is when, if you feel that way, then Einstein's idea is better because he's saying there's like a fabric, like a cloth, so the earth, the hay, and there's like a cloth, and then the sun distort the cloth, like, okay, this is the sun, it distort the cloth. I should have drawn it a little lower. And that caused the earth now to be sliding down towards the sun. That is what he's trying to say. Anyway, I'm deviating too much there. My point is, we are the only people who still use this word, right? All the other sciences are using this because people are coming up with different explanations. They no, or that explanation. This can explain the thing better, and that is why we end up where we are, right? But in mathematics, largely so. I'm not saying in every area of mathematics that's true, but in the pure mathematics especially, we still have theorems. All of you know the Pythagoras theorem, all the circle theorems, in geometry that you learn at CXC and so. It is only here we still have theorems, right? And these theorems, and so they don't contradict any of the axioms, right? No, they're built on them, right? They're built on them, and you don't find that, well, you're going to find any piece of mathematics that goes against everything else, right? No, they all are in harmony, which is a beautiful thing, right? That's what you want. Yeah. So back to the simple equation business, right? Yes, you know all the shortcuts and so, and so let me put a more complicated one. Maybe you want to solve something like this. All right, so we go. Did I say complicated? Maybe something like that. And yes, people are going to tell you, man, oh, you take over the -3 and it becomes 8 plus 3. So x equal to, what is this, 11, right? What I'm trying to tell you is that this here, right? it's not real mathematics then. It's a shortcut that has been developed and people accept it and we're doing it, right? What in effect you're doing is this: you're adding 3 to both sides, right? You're adding 3 to both sides, right? And this becomes 0, so you get x equal 11, right? I'm saying that nothing is wrong with this in that you can do that. I ask you to solve an equation, you do it like that. I'm not going to kill you. I'm just saying you must know behind your head that it is really the axiom, right, of, that an equation is a balanced relationship. And any alteration you do to one side, you must do to the other side to maintain the balance, right? And you get all kinds of them. I know you have okay, let me see another one. Maybe one that involve, okay, what is it? 2x equal to, let's say, 16. Let's go there. So what do? You normally say take down this thing and you divide, right? Something like that. I don't know. Yes, you get x equals 16 divided by 2. Again, I don't know which operation this is, where you take down x and divide. I don't know. There's no mathematical operation like that. What you really mean is that you are dividing both sides by 2, right? And one thing, nothing wrong with you writing a statement, right? That divide, nothing wrong with saying divide both sides by 2, right? So you do this, 2x over 2 equal to 16 over 2. Therefore, you do a little thing here, right? And that implies that x equal to 8, 8, right? Remember when you were writing, I know again, especially because you're used to multiple choice and so whatever you work out to get the answer, you scribble anyhow. And so what is lost largely, I notice now among students, is them writing very clearly. And I think that is suffering a lot in the sciences. People's ability to articulate, their ideas and to explain what they really mean to readers. Why? Because we get used to this thing where we cutting and pasting. Nobody is developing their creative side where they're saying, look, let me say this thing in my own words. And that's why we don't understand stuff very clearly. The reason why is we taking somebody's way of saying it and we cut it, we paste it, we give the lecturer to mark, and that's it. Right? So we're losing that ability to, explain things in our own words. Right? When we're writing for people now, we just jump. Sometimes we take this here and I don't see this. And you go straight here. And a reader, remember, okay, I might know what you're doing. But then others might not know, well, what are you really doing here now? Especially if they see all this working. So what the hell is all of this? What's all of this? So it's good for you to say, say what you're doing. Say what you're doing. Right? So people can understand, oh, I think I know what a person did. Right? You understand? And this step-by-step, as a matter of fact, this step-by-step procedure is what lends itself, I hope those boys from the computer science class is here. This step-by-step process is what lends itself to you writing code that can do equations, because they have all these math solvers online now, right? The boys are here, those guys, those TSC people, computer
Yes,
science
sir.
people. Y'all are here, all right. Y'all are 10 sitting
Yes,
down
sir.
right now. Y'all are 10.
No, I'm at home. No, sir, I'm at
No,
home.
So what
yes,
happened to your
sir. I'm
class?
at home.
What happened to your class at 5 o'clock?
Uh, we don't have any today. It's tomorrow.
What happened to the class? But the lecturer
No,
moving
don't.
to tomorrow? What happened to the class?
We have an economics class today at 5.
Oh, so we are doing economic.
Oh, they have 1 or 2 of you who doing it, and the other set choose stock 1100.
Yes, sir.
Okay.
Yes, sir. It was an elective course.
Yes, I know. Yes, so a few of you choose economics. All right, not bad. That SOC course, what's the name of it?
Study of society.
They what?
Study of society.
Great, yes, that's a very good course. You know, how society works. The economics course is a good one too, you know. Helps you to understand what's going on in the country and the prices. Yeah. So I want to, you know, advocate, and I can only talk, you know. I'm seeing the effects of you know, computer technology, and so where you can look at my handwriting and know that I've lost it totally. I have a friend who he sent some old notes for another course. Somebody asked me to do an extra course. So he shared some. Man, you see this man handwriting. This man should be an artist, right? Or handwriting, the ability to write is lost, or creativity to be able to, you know, paraphrase and put things in our own words. Some of y'all get a lot of problem with plagiarism, right? Because if you can't take a chunk of information and put it in your own words, it's telling your reader you don't understand. And if you do understand, you're lazy to create, right? Well, once you know, you can't take what a piece of a chunk of information, a paragraph, and put it in your own words, right? Your creativity side gone, all your ability to comprehend and to express yourself is gone, right? You're going to have a lot of problems as you move forward, right? At UG. Yeah. So let's go on to some maybe let's try another one. Let's say you have to solve something like this. Let me go with, all right. All right, there we go. I don't know. I know what does this one short out, right? Look at this one now. Any suggestions? What do I do here?
Firstly, you would subtract both wait, yeah, subtract both side by 4.
All right, look, let's analyze that statement. You're subtracting both sides by 4. What do you mean by that? I'm not, my intention is not to embarrass the person, right? I'm just showing you again how, because, you know, nobody correcting you, and maybe the teacher never asked you to express yourself. He said to subtract both sides by 4. Does that sound mathematically correct? The way he stated that? What should he have said? Subtract both sides by 4?
Subtract 4 from both sides.
Yes, you got to watch what certain words may convey. And these things are going to become important when we go to word problems in a moment, right? Like when you say, okay, you say subtract, right? You don't want to use the word by, because this word seems to be connected somehow with maybe multiplication, right? Right? So you might talk about subtract from, not by, right? So I'm not embarrassing my friend. I'm just telling you that you got to watch certain words, because when you start confusing these words, you're gonna have trouble with word problems. So yeah, that suggestion was good. You subtract 4 from both sides. Okay, let's do that. So how are you gonna do it? You want, maybe you can put it there. Do you do it there, or you usually put it 4 at the back here? Some people can do this. 4 minus x minus 4. Oh, this is supposed to be 4. Some people do that, right? Among to the same thing. So this is going to be 0. You're left with minus x equal to 1. So is our problem solved here?
No, sir.
So we subtract both from both sides. Use that word, right? You subtract from. Don't subtract by. You divide by. You multiply by. Right? So what do we do now? What do we do with this here? This my negative sign. Any thoughts?
Um, I would say you no, not multiply. I mean, divide both side with uh, -1.
Okay, so again, he's saying something. -1 equal 1, right? He's saying what? Multiply with, multiply with. No,
No, I said
no.
divide.
Listen to me. Divide. All right, divide with. You use the word with. What's the name? Damani Herod.
Yes, sir.
Remind me to give you 1% for taking all this embarrassment, right? 1% for having to correct
Thanks.
you, and the class might say, why don't keep your mouth shut? You don't worry them. You don't worry them. I'm giving you 1% for being bold enough to participate and sung wrong and be corrected. It builds character, right? You are going to learn. And they learn, just imagine they're learning from you, but you got to get marks. You got to get marks to be bold enough to say even the wrong thing, right? You get me,
Yes.
Damini? You just remind me if I ever forget, right? So if you see you get
Okay.
74 out of 100, I'll give you that 1, right? I might even give you 2.5. You understand? Yeah. So
Thank you, sir. Thank you,
we
sir.
usually wouldn't say multiply with or divide. We said divide by, right? Or multiply by. And we can do either of the two. We can either multiply by a -1 throughout, right? So it's the same thing as multiplying this side by -1 and multiply this side by -1, maintaining the balance. This is going to turn out to be x. That's going to be that's going to turn out to -1. The same effect is if you were to divide both sides by -1, right? So you have minus x divided by -1 equal to 1 divided by -1, and you'll get x is equals to -1, right? Yeah, good. I like that. Herod is your last name, Herod. Very good, very good. Right? Don't be afraid, man. Don't be afraid. You participate, right? You're computer science.
Yes, sir.
You know that's a good trait you have. You know, right? If you see a team of you, maybe writing a chunk of code to do something for a client, you got to get somebody who in the let me put this another way. Okay, there might be these guys who are really good at coding, you know, but there might be one person who, okay, he's not so good with coding, but guess what? He's thinking about the user, right? And he looks at the website and he says, you know what? No. I know you all can, you know, you type in all this code and the website looks this way. But think of the user, you know, and the user friendliness of it. You know, and then you start to tell them, watch, could we do it this way? That people don't like when you do this and when you do that, you know? Like I visit a website that I use a lot. And recently they changed it up, and boy, I don't know what they do with the website, right? They mess it up. So the user now have a hard time. It's a website with cars where you can go and search for a car to buy it or what, right? And before time they had all the different cars in alphabetical order of a particular brand that you can go and say are A, all the cars starting with A, and what all the cars B. Now they have just a single search bar now. And if you don't know car name, well, you can't find nothing, which most people don't know car name. All we know in this country was what we know in this country, Canter, and what car we know in this country, Premio. So if you don't know any other name, you can't find any other thing. Right? So they made a website as though the people who are using it are so familiar with cars, they know the names of all of them. So you don't know, you can't find. You know, so it's good to have somebody in that group that says, hey. Yes, you're writing code and changing up websites every week and so, but think of the user. You know, so it's good to have somebody who ask those questions and say, hey man, when we finish though, will the user find it easy to navigate and so on? That's why I guess you all know of people, they hire people, to test websites out and to give them feedback if they like the interface, and all of that is work. Yeah. All right, let's do another one. I want to finish before 5 o'clock for y'all class. Let's say you have one like this. Okay, x over, okay, like that. Right, let's say like this, right? And I think one of the first thing people would do, they take this thing, right? Put some one under here, and they do something called cross multiplying, right? And I get x equal 30. Again, okay, it's acceptable. Everybody does it but there is no mathematical operation named cross multiplying, right? There is no mathematical operation named, sir. What you're doing, the shortcut you're doing, you're actually taking this and multiplying both sides by 5. Sorry, by 6, no? It's by 6. Right? So you're maintaining the balance, right? You're maintaining the balance. You're multiplying both sides by 6. So you get x equal 30, right? So while everybody accepts it, I want you to understand what you're in effect doing. Right? What in effect you're doing. Because let's say the boys who are writing code to maybe they're writing a little bit of code that would solve such an equation, right? They're not going to find some kind of code or some kind of command that will make the program do something named cross multiplication. They're not going to find that, right? What they're going to find is that they're going to find that, okay, there's something that says that you can take this denominator, whatever it is, right? So the program might end up, let me just show you what the program might end up looking like. So you get x over box. Let's just say that equal to another box here, right? So this box is different from that box, right? The underlying code will tell you that. So it depends on what somebody puts here and here. You will tell the code is going to tell the computer to here what? Multiply this here by what is under here and multiply this here by what is under here, right? You see? So it's going to do it the way the axiom tells us to do it. It's not telling you to cross multiply, right? The computer language doesn't have anything that has to do with cross multiplying because that's not a mathematical operation, right? So boys, I know they have all these things online and so, but you must try. You almost in your own sweet time, try to write little chunks of code that will do stuff, right? Don't say that, man. Don't say that, there are all kinds of programs out there already. You need to learn how to do some of it, right? And the reason why is that you might have a client come by that would ask you to do something that is not out there. And I'll tell you, let's get to some more. We're gonna talk about those ideas a little later. You have to solve something, all right. You got these here. Right? Let's say you have something like that. Again, now the process of doing, or applying the axiom step by step becomes very lengthy. And I think here is where most people will go for the shortcut. They'll take this -3 over here, and they'll take this 2x over here, yeah. And they'll do this, right? And this turns out to be, okay, equal 12. Then they, take down the 3, divide, get x equal 12 over 3. Yeah, people do that shortcut, right? All I'm telling you is that just realize what you are doing, right? Basically, what you're doing is you're taking 2x away from both sides, right? And you're taking two. Oh my! Let me do it back here. 5x minus 3 You're taking 2x, all right, if I am to do it in, so you get 3x minus 3 equal to 9, right? And then the next step, you add 3 to both sides, so you get, right? And then you end up with 3x equal 12, and then you divide both sides by 3, so you end up with x equal 4, right? So yeah, the shortcut is acceptable. I'm just saying, know how you apply the axioms, right? That's all I'm saying, right? That's all I'm saying. And then equations can get like, okay, you can involve some brackets, and so, all right, let's go with something like this. Okay, let me use 8 here. Like that. What would you do here if you have to solve something like this? Any ideas?
No, sir. The first thing I would do is to multiply the brackets by the 2.
Okay, you use the distributive law to remove the brackets, and so, all right. Any other approach? Anybody's thinking of anything else?
Sir, you could divide the 8 by 2.
Yes, you can do that too. Yeah, you can divide both sides by 2, right? If you want to write it in words here, divide both sides by 2. And mentally, right? Abstractly, you just say, well, that will result in 4, right? And so that can work too, right? And then, well, you take the 5 over, you subtract 5 from both sides, you get 3x equal to, sorry, not subtract 5, add 5 to both sides, right? And that'll become 9, and then you divide both sides by 3, and you get 3, right? So whether you do it the other way, or this way, it's not a problem. Yes, somebody was saying something? Hmm? Okay. Change your mind?
Sir,
Uh-huh.
so um 5 to both sides, right? How does that like can you explain that?
What do you want me to explain? I didn't get that.
So first you divided the 2 on both sides, and then you had to add 5 on both
All right, just
sides.
pause.
Why
You
was it
divide
like that?
both sides by 2. Don't say divide
Yes.
2 on both sides, right? You divide both sides
Sorry.
by 2. Yeah. Uh-huh.
Right, yes. Divide both sides by 2,
We got
and
this.
then you added 5 to
Adding
both
5 to both
sides.
sides, right? I didn't write it out, but yeah, all right. Plus 5, 4 plus 5, right? So this becomes 0, and you're left with that equal 9, which is that, right? And then you're dividing
yeah.
both sides now. You can, I didn't write out the words. Divide both sides by 3, right? Or you put this, right? So x is equals to 3. Right?
Okay.
And then, they can get more complicated with fractions and so. Look at this one. Let's just throw out one out here. Maybe something like this. Fractions now. What do we do here? Any ideas?
Can we find the LCM?
LCM, yeah. Why you want the LCM? LCM. Oh. Somebody says find LCM.
Yeah.
Of what? What is it? 3 and 5 or?
5 and 7.
Yes, the denominators, right?
Yes, sir.
Good. So I think it's 5 and 7, which gives us 35, right? And again, there are several approaches to it. Some people multiply everything, multiply both sides by 35, right? So you can take 35 and multiply everything here. Equal to 1 over 5 times 35, you can do that. I get what? We'll get what? 7x minus 15 equal to, what's that, 7? 7? And then we know to solve something like this, right? I wouldn't go through the steps. So, simple equations can get, a little more complex and involve fractions. The fractions can be, the x's can be on both sides and so. But the key, like maybe do another one more. Let's try one. We have to solve, let's say we have to solve, all right. Right? And what will you do here, by the way? Any suggestion?
Will we be grouping like terms?
Okay, that's a good suggestion. A lot of people go straight to the LCM thing and multiply everything by the LCM. Nothing wrong with that. But I like alternative approaches, right? Where you can, okay, what you're saying, you can bring this over here and bring this over here. So you have 7/8x minus 4/5 x equal to, okay, a quarter plus 11 over 4, right? Some people do that. And then they'll do this subtraction. So you probably bring out the x outside, factorize it out. 7/8 minus 4/5, right? What's this? Equal to, what's this? 12 over 4, right? They'll do this little bit of arithmetic. Anybody doing it fast? What's the LCM of 8 and 5? 40? 5 7s, 35, 5 8, 5 4s, okay, 32, right? So all of that becomes what? 32 from the 3 over 40 x, right? Equal to 3. So x then will be equal to 3 divided by 3 over 40. So that becomes what? That is some right. Did we do that right? Yeah. X then will be equal to 3 multiplied by 40 over 3. That and that goes. X then equal 40, something like that.
Yeah.
It's just
Yes,
one
sir.
approach, right? If you have something else in mind and it works, it works. You have several approaches. Some people multiply every single thing by the 40, because they think that 40 is the LCM, and that gets rid of all the fractions, and you're left with a nice, an equation without any fractions, and they work from there. This one trouble you? As I said, let me do the one where you multiply everything by 40. Let's write it back. So you got 7. And as we said, we multiply both sides. Some people write it like this, by 40 being the LCM of everything, right? And when you multiply that, you'll get 35x minus 10, I think. Yeah, equal 32x plus
Yeah.
110, or yeah, right? And I guess you can take it from here, right? You take this here and you take that there, right? Shortcut now, right? We're jumping the axioms and so on. So we end up with So we end up with 3x equal 120. X then equal 120 over 3. X equal the 40, right? This is all CXC mathematics. This is not university mathematics at all, right? So you were supposed to be able to handle this kind of thing from since then. And some of them can get a little more complicated. I'll leave some of them there. They're in the tutorial worksheet, and I hope you try them. And you don't need answers for them really. You can always know. How do you know that your answer is right? So you solve an equation and you find x equal 1 or x equal 10. How do you know that the answer is right?
Plug it back into the original equation.
And it should. And what should happen?
It should balance.
Yeah, I'll use that word. It should balance, meaning whatever the right hand side works out to be, the left hand side should work out also to be that, right? Very good idea. Yeah. So you don't need an answer sheet and you run to the textbook, check on the back seat, mate, right? No, you can know, right? It has a way of telling you. Good. Just a little bit on what we call simple inequality, right? Simple inequality, right? Basically, oh, by the way, I made some notes available to you, right? And I think the note says you solve them just the way you solve equations, except, and this is the piece everybody just forget, except if you multiply or divide throughout by a negative number, the inequality sign is, or should be reversed, right? So you're proceeding just like you're solving a simple equation. The only difference here is that if you were to somehow you end up in a situation where you want x to be greater than something or less than something, what? You don't want a minus sign in front there. So you have to divide throughout or multiply throughout by some negative number. Remember to reverse the inequality sign. And it comes from that axiom. I keep using that term over and over, right? That axiom, the monotonicity axiom, right? That says that if A is greater than B and C is greater than 0, meaning C is positive, right? Then AC is greater than BC, right? The monotonicity axiom. All of this comes under something called the order axiom. This is one of them, right? Which tells you, you have to somehow maintain order on the number line. Number line the real number line in particular, if you don't maintain order, you break the rules, well, you're going to do a lot of mathematically incorrect things, right? So they're saying that you have two numbers, and the relationship between these two numbers is one is greater than the other. If you were to multiply them throughout by a positive number, it maintains the order. However, if C is less than 0, then AC is no longer greater. It will cause this. It will cause a reversal. And you can check this, right? You can please check this. Take two numbers, right? Let me take some numbers. I'm trying to do it here. 2 is greater than 3, right? And let C be equal to 5. So 2 multiplied by 5 is still greater than 3 multiplied. Oh, what am I saying? I'm saying 2 is greater than 3, and not a soul and tell me nothing. Sheesh, man. All right, give me a second. Like y'all drop the sleep or what? Yeah. 3 is
Sir,
greater
you
than
know, his
2.
maths
Yeah.
as 2 could be great. 2 won't be greater, but you could use the 2 as like a symbol and settle that, yeah, this is greater.
Yeah, so it maintains the order, right? Multiplying by a positive number maintains the order. However, look over here. Let's go with, all right, 3 is greater than 2. And let C be equal to -1. Look at what happens. So if I were to multiply throughout now, multiply both sides, I'll get -3 and I'll get -2. So should I put this or should I put that?
Switch the inequality sign.
Yes, you have to use this. This is the right thing. The inequality sign is turned around, right? So that's a kind of intuitive explanation. There's a deeper and there's a proof in those higher courses to show you the same thing. But intuitively, you can see it with just those numbers that I use there, right? And it is for that reason then that if you were to, have an inequality, and let me just maybe do 1. Let me do 1 maybe. Maybe you have some of it. 1 minus 5 is, sorry, what am I doing? Yeah, 1 minus x is, let's say, less than 5, something like that. Right? If you're smart, you want to avoid all this negative thing, and so you can take this over here, and you can bring the 5 over there, and you end up with 1 minus 5. This minus x is going to become x, right? So minus 4 is less than x. So you write that back as x is greater than -4. Alternatively, you can do it the other way, where 1 minus x, and you subtract 1 from both sides, right? So you end up with minus x is less than 4. And then you multiply now throughout by -1, right? Multiply everything by -1. When you do that, you know what has to happen to this, right? So you're going to get -1 by minus x is going to give you x. This has to switch around. That becomes -4, right? So you end up with the same solution as this. But just remember that one little bit in the rule, right? That if you multiply throughout or you divide throughout by a negative number, the inequality sign has to be reversed. Right? Good. Let's talk a little about another set of equations now. And we want to talk about that's a M, simultaneous, linear, I'll stick with linear for now, equations, right? And here is where you have two lines, basically. And you want to find where they intersect, right? So maybe I can throw up a pair there. Maybe you have 3x plus y equal 18. Maybe you have 2x minus y equals 7. This is really a straight line. If you were to draw this is a straight line, right? If you rearrange this, you get what? Y equal minus 3x plus 18, right? Y equal mx plus c. Do you see the similarity? So this is really a straight line, and this is a straight line. And the solution of this equation lies where these two straight lines intersect, right? So if x is whatever here and y is whatever there, that's the solution to this equation, right? We're only going to talk about two methods in this course because in your other courses, you're going to deal with matrices and all of that, right? We're going to only talk about the method of substitution, and the method of elimination, right? We're only going to talk about these two quickly, right? Good. So maybe we can take substitution first, right? All right. So let's move this a little here. Good. So in substitution, the basic idea, I'm not going to solve the whole thing, right? The basic idea, you take one of the equations. Okay, let's call this equation 1, call this equation 2. You take one of them, any one. And by the way, substitution tend to work, or it can work in any case, but it's just that in some cases you can end up with some horrible fractions and so. But substitution works well when maybe one of the unknowns, right? One of the variables has a coefficient of 1 in front. It tends to work better, you know? It lends itself to a smoother solution, right? So we can take any one of these. Maybe we can take equation 1. And from equation 1, you can see that y will be equal to 18 minus 3x, right? And we can call this equation 3. Our next move is to take the value of y now, because we found an alternative statement for y here. And we can put that here. We can put that here and look at what happens. So we can substitute y equal 18 minus 3x in equation 2. And look at what happens. You end up with 2x minus, well, y is this now, right? 18 minus 3x equal to 7. And what do we have here? That's a simple equation, right? That we were learning how to solve all the time. I'm not going to solve it, right? Yeah. An alternative is what we call elimination. The method is called elimination. So let's maybe write that back, right? Y'all get this one? This is not very difficult. There are some tricky ones in the worksheet. I wouldn't show you how they can be done, right? Where the coefficient of y might not be 1 here, yet the instruction says you must use substitution. but I want to see the idea that you are going to come up with. Most of you are going to run to AI to do it, right? But I'd like for you to, if you can, remember the whole idea behind this course is to develop your thinking ability, right? To solve problems. And if you have a way of any problem face you, you run to AI. I don't know. I hope later on you don't run to drugs. I got this problem. Go buy a joint for me, boy. AI can be that, can have that effect on you. Oh gosh, what's happening here now? I was having this problem the other day. It's not moving now. Space bar is this. Okay, all right. Just give me a second. I might need to. Something was going wrong with whiteboard. It's not moving the I don't know why it's creating these lines. All right. Just let me close let me close that whiteboard. I hope another one. I think Zoom has a whiteboard too, right? Okay, I'll use their whiteboard for now. Please don't write anything on it, right? Good. So let's do back that same problem. Oh, I need to. Yeah, please don't write nothing, right? Yeah. So we have to solve this. I said don't write anything, you have to erase that thing. 3 plus y equal 18. So using elimination, this is a very, very easy one to do in that this is what we can do. We can add these two equations and look at what happens. 3x and 2x will become 5x. This positive y and this negative y becomes 0. And this becomes what? 25. So we end up with this, which implies that x equal 25 divided by 5, which is 5. Right? Now that we have x is 5, we can substitute now in any one of these to find y, right? So maybe you can use, equation 1, substitute x equal 5 in equation 1, and you get what? 3 by 5 plus y equal 18. And, well, you can see that y is going to be 3, right? This was very, very simple in that the coefficient of y in both of these equations lend itself to an easy solution. In this case, you add them and it works out nicely. At other times, it may not be that simple, right? It may not be that simple. Maybe let me give you another one that. Let's do one that. How do I scroll this? I don't usually use clear page. All right, but I just clear the page. Look at this horrible looking. What will you do here if you have to solve something like this? Oh, this x is not underneath here, right? I kind of. Where's the eraser? Is this? So it's 2/3, right? Yeah. Any ideas what to do there?
Sir, you
I
can use
would
the first equation.
What will you do?
Use the first equation to find y.
I think that'll be rather complex, you know. I'm talking about using elimination, right?
Oh,
So what I think is happening is that you want to get to this elimination or substitution right away. But you have another problem here, right? You understand, not all your problems will be what you see in high school where you say, okay, we can right away go to substitution or elimination. Here, some groundwork got to be done, you know? So you know, it's like Guyana here, who is doing all kinds of things? Well, what is this now? Yeah, yeah. Yeah, in Guyana here, you know, sometimes you buy a piece of land and you just can't go and build a house on it. Somebody erase the thing, boy. Man, I need to set this thing that nobody can change. No, what is this? Um, okay. What do I need to do here? Hey, don't somebody just okay, we had this here. I lost my thoughts and all. Yeah. So you can just start you know, working on elimination or substitution yet. You have another problem to deal with, right? As I was saying, you know, in Guyana, you buy a piece of land, you can't start build house yet, right? You got to go and clear up the place. You may got full little land, all kinds of things you got to do, right? Some groundwork, and that's this equation here. It's problematic. It has some fractions. Therefore, you'd have to do what you were doing earlier when you were doing simple equation, where you got to get rid of the fractions, right? By multiplying by the LCM and so, right? So the LCM here is what, by
15?
15, yeah. So you multiply everything by 15 and you end up with, what will you get? 10x plus 12y equal, this is a big number, right? So now you have the two equations there. I want to take this. Let me see if I can pause this. I was supposed to pause it and not stop it. All right, yeah. Let's see what will happen. Yeah. So now we have our two equations, right? And well, now we can use the old methods now. We got 3x minus 5y equal minus 16, and you have 10x plus 12y equal to 90. So they look nice now, no fractions. The bush clear up, you know, and we can now solve them the usual way. So if we're going to use elimination, well, then we're going to do a lot of work now, right? You have to choose what you want to eliminate, right? Isn't that what you do? You have to decide what will we eliminate. Which one what you all want to eliminate? The x first or the y? Which one? You tell me. You want to eliminate the y's? All right, let's eliminate the y. Eliminate y.
Why, sir?
And how we do that is that we take the coefficient of y in this equation and multiply that one. And take the coefficient here and multiply here, right? We're not going to do the negative. We're going to use the 5, right? So we'll take 3x minus 5y equal minus 16. And I'll multiply that by 12. And then I'll take this one, 10x plus 12y equal to 90, and multiply all of that by 5, right? And what will we end up with? How do I scroll this thing? I've never really used this. Oh my, not like that. Okay, yeah, like that, right? So tell me what you'll get. Tell me what you'll get when you multiply. Let me write them down here. What's this? 36. Help me now. Multiply this for me. Minus 16 by 12.
Negative 192.
192 here.
192.
Okay, and this will be what? 90 by 5.
450.
450.
Good. One of them, this is negative here, right? Good. So what we can do is add, right? We add. That will get rid of the minus 60y and the positive 60y. So this is what? 86x equal to, could you do this for me?
256.
256, right? And that should give you
258, sorry. 258, sorry.
Okay.
Yes, 8.
So x supposed to be 258 divided by 86. I hope you get a nice number here. What do
3.
you get? 3? Oh, great. We get a nice number. Good. And now you can take this 3 and substitute back it in one of these equations, right? Here or here to get y. I use the example to illustrate that sometimes, you're eager to go and do substitution or elimination, but sometimes you have to do some cleaning up first, right? You have to do some cleaning up, right? Where, like in this case, you had some horrible looking fractions here that you had to clean up. And if you don't clean it up, you can't proceed, you're going to have something very difficult to deal with, right? So keep that in mind. And those are the only two methods we're going to talk about for now, right? As I said in your other courses, and so you'll do matrices and you'll learn some other methods and so. We are going to, let me see, yeah, when I do simultaneous equation, when one is linear, one is nonlinear, we will see the geometric side of things where we're going to have, some graphs and so on. You're going to see the solution is where the line and the curve intersect, right? And you can actually make sense of this as well, is that the solution to the simultaneous equation is where the two lines intersect, right? Good. Lastly, I want to talk about, I want to talk about the matter of word problems. Word problems. Right? Word problems. And this has to do with whether we're dealing with word problems leading to simple equations or word problems leading to simultaneous equations. I think this is what puzzles everybody. And you are wishing in your mind that I'll give you some formula that you will apply and it will solve every word problem. Is that what you're imagining? Is there an honest person in this group who will tell me that? That you wish you were given, a single approach, a set of steps that you can, apply, and you are going to solve all word problems in this whole wide world, right? What is happening? Aliyah is playing Hansi with her sister. All right, like these things happen. Yeah. Okay. So I think I want to use maybe a word problem or two from the worksheet to best explain what I'm talking about, right? So give me 1 second. Good. I want to just go to maybe a worksheet. Give me 1 second. Not there. Give me 1 second. Tutorial worksheet. Okay, good. Good. So you're with me, right? You're seeing this? Word problems leading. Okay, this one says leading to simple equation. This is the worksheet I gave you. Everybody can see this?
Yes, sir.
Yes,
Good. So I'm sorry to disappoint you that there is no one set of steps that I can give you that will work for every word problem. You know, if you watch these word problems, first of all, you're seeing what? This one seemed to be, it involves some geometry inside. Do you notice? This one seemed to be some geometry. The second one seemed to be some number theory, right? The third one got to do with what looks like something in physics, kinematics, that deals with speed and so speed, distance, and time, it seemed like, right? This one seemed the same way. This one is some geometry, another number theory. This one got to do with some arithmetic, right? You notice? So the trouble with these word problems is that there is no one approach, right? And there's no fixed set of steps that I can tell you that you can follow slavishly and solve any one of them. They're truly problems that will put you to think. And what you need to do is you want to try to see if you can model the problem mathematically based on the information you're given, right? So that's your aim. You want to model the problem mathematically, right? And maybe if you want to use maybe one of them, all right. Let's go to the first one. I think one of you might have this problem to do, and I shouldn't be working it out. But let's see, right? Let's say you have to work this problem out. Good. So you want to, as I just told you, try to model the problem. The modeling, what can help you to model a problem is if the problem lends itself to a diagram, draw a diagram. Draw a diagram. Use the information to see if you can model it. If you can model the information on a diagram. There are questions that, no, it might not lend itself to a diagram. Well, you have to find something else, some other way to do it, right? But if you can draw a diagram, it will be good. And I can tell you this, in the past few years, I teach both mathematics and some physics courses. And I'm noticing that drawing diagrams for students to conceptualize a problem is missing from mathematics. And I'm talking about teachers doing mathematics and physics and no drawing. I've noticed it for the last 3 years. I want to know where has all the diagrams in mathematics and physics gone. All I see is numbers and words. I don't know where to bring in all these words and get rid of diagrams. So as I said, you're trying to model this thing. So if you can draw, they're talking about, okay, here, there's a rectangle involved, right? Mention is made here of a rectangle. So it might be good for you to draw a rectangle, right? That's a model. You're beginning with a model here, good, right? It's talking about the rectangle is 3 times as long as it is wide. Now, what you want to do now is read meaning into what do these things mean mathematically, right? So it says that the rectangle is 3 times as long as it is wide. You have to interpret that now in mathematical terms, right? It's talking about long and wide. What two mathematical terms, or I should say geometrical terms, are associated with long and wide?
Length and width.
Very good. So you
Length
see,
and breadth.
that's another key, right? That's another key. Could you translate, right, the words now into mathematical language? So they're talking about long, so we're thinking about length, and here we're thinking about width, right? So we can name it, all right. All right, if you want to go with W here and L here, all right. But this thing is also telling you that the length is 3 times the width. So what you could do, you could say that this is 3 times W, right? Just to get everything in terms of W, right? So far, we got a diagram from this word. And we got, all right, from long and wide, we got 2 unknowns, W and L. And we related W and L somehow mathematically, and we say that L equals 3W. So you see, you're able to model the sides of the triangle, right? Now you're given some more information. They say the perimeter is 56 meters. So could you add this to the model now? Add it to the model. So you know that, all right, perimeter is the distance around. So down here is 3W, down here is W. So it'll be 3 and 3, 6 and 2, 8W equals 56, right? So they ask you to find its dimensions, right? Well, in other words, you want to find W and you want to find L, right? Well, you can solve this. This is a simple equation. You solve for W, you get W, and then you calculate L, right? So whenever the problem lends itself to diagram, you draw it, right? Look for keywords. Look for keywords. Find out what do they want you to find, right? In this case, you want the dimensions, the length and the width, right? And what you can probably do from the beginning, you can probably say, or when you draw your diagram, you can say, let W represent the width of the triangle. Let L represent the length of the triangle. Sorry, what am I saying? Width of the rectangle and length of the rectangle, right? And then you look for what information connects now. These are known, right? And in this case, the perimeter connects them. And then see if you can model it again by some equation or inequality, or, well, in other cases, you get a pair of simultaneous equations and so, right? That's what you want. Not all of them will lend itself to that. Here, look at this one. You have something that involves number theory. You have to remember now, you know? So this one says, find 3 consecutive even numbers whose sum is 84. So you're talking about even numbers. So you're looking at 3 of them, right? So you can probably say, all right, like the computer science boys, at the beginning of your program or your little code that you're going to write, you're going to declare your variable. Let n be the first even number, right? You know that is required, right? Good. I don't mean the first even number 2. I mean even number of the 3, right? If you want to write out that, let n be the first even number of the 3 consecutive even numbers that we're talking about, right? I'm not going to write all those words out. So good. N. So The next question is, okay, if the first one is n, what will be the next one? And here's where your knowledge of number theory is coming in now. So you declare your variable. What if the first one is n? What will be your next even number in line? And here's where your knowledge of number theory, if you don't know your number theory, you're going to
N
be
plus 2.
very good. Yes. Why? Because you know that even numbers are kind of spaced out by 2, right? So the next even number will be n plus 2. And what do you think the next one will be?
N plus 4.
N plus 4. And they tell you a piece of information that the sum of these even numbers is 84. So n plus 2 plus n plus 4 will be, what I say, 84. And you have a simple equation to solve, you know? And then you can, find out, well, remember they told you, you have to find the 3 consecutive even numbers. So when you solve for n, well, then you will figure out what the 3 numbers are. Must always read what the people are asking you. So from problem to problem, it might deal with a different area of mathematics. It might even venture out of mathematics, go into, consumer arithmetic and even the business areas and the sciences and all of that, right? I mean, we'll try to give you problems that somehow you were exposed to that kind of thing before, right? We're not going to go give you a problem that you have no idea what the people are talking about, right? Because I'm sure you did. You looked at speed, right? You look at that expression. What is it? Speed is equals to distance over time. I think that, I don't know if that one is related to this problem, but this here is a good relationship that might be of use there, right? Understand? This one here, okay, talking about a triangle, you know that, okay, angles in a triangle add up to 180. Maybe that is helpful there. You understand? So you are going to draw on background knowledge and you're going to try your best to model the information that is given such that you can make up, well, in this case, your model is going to lead to simple equations. In the other exercise, it's going to lead to simultaneous equations. You're going to solve them, and then you're going to, give the people what they ask for, right? Don't be satisfied with just the solution. You may get n equals something, but that's not what the people want. The people says, give me 3 consecutive even numbers. At the end, make sure you answer the people, right? And don't just be satisfied with solving the model that you created, right? So yes, I am a little sorry that you want me to give you some definite steps, and it will work for every word problem. No, it might not, right? As I said, you might need some background information, right? I mean, the problems we're going to give you, you were exposed to that background in high school, right? I mean, in the real world, if you ever have to do something like this, I mean, there are people who are trying to, when they do their research and so, right? For researchers, something you never hear of something, right? And you have to go and study. I remember when I was doing my research for my master's degree, I stumbled, you wouldn't believe me, this is the last day of school, right? Of the semester. I don't have a research idea. Sorry, it was the second to last day. And I was lent a journal. And the journal had an article on personal epistemology and mathematics. So I never heard the word before. I never heard of epistemology. But when I read the article, I liked it. And I said, you know what? I'm going to search now. I'm going to research what do you mean by epistemology, right? And basically, epistemology, I found out later on, has to do with your beliefs about mathematics. I mean, well, epistemology can be your beliefs about anything, but in this case, I was dealing with people's beliefs or students' beliefs about mathematics and how that is affecting how they learn mathematics, right? And I had to research. And I remember my supervisor told me that you do not write a single word until you have done about 3 months of research. And the guy was so right. I started to read about epistemology and mathematics for months. And then is when I said, you know what? I think I know enough to write my first word. Right? And I built up the research from there. And the same thing is going to be true of you, right? I mean, for now, we're going to give you things that are familiar. You can see we're talking about everything that is familiar with you, right? Look at what's happening. We're talking about rectangle, even numbers, somebody walking and riding around the place. What is this? Fractions, somebody buying at a shop. These no-brainer type of situations, right? So yeah, we're not gonna give you things that you never heard about. I'm just saying that maybe later on when you go into the real world of research and so you will see that you'd have to really study things, right? You have to really study things. A lot of the things you're going to learn in your degree is going to be useless to you. And you'll be surprised to know that you end up in an area where you know nothing about. And you have to learn from scratch. You might get a job, I'm just saying, you get a job in a place. Like I have a friend,